Welcome to the pressure levels and terminology aspect of chemical process utilities. Now let's have a brief outlook that what we are going to cover in this particular lecture. Since pressure is a very important phenomenon in all chemical engineering operations, so we will discuss about the pressure, concept of pressure and other related definitions which are attributed to the pressure. Then we will discuss about the concept associated with the behavioral aspect of gases. And apart from this, we will discuss certain numerical problems attributed to this particular approach. So let's talk about the different definitions which are closely associated with the concept of different pressures and different other aspects which are attributed to their utilities. Now let us talk about the atmospheric pressure. The atmosphere that surrounds the earth can be considered a reservoir of low pressure air. Its weight exerts a pressure that varies with temperature, humidity and altitude. And this particular phenomena is very important while considering the pressure approach to the various engineering applications. For thousands of years, air was considered as weightless. And this is understandable that the net atmospheric pressure exerted on us is zero. The air in our lungs and the blood in our cardiovascular system has an outward pressure equal to or sometimes perhaps slightly greater than the inward pressure of outside air. That is why there must be a balancing between the two objects. Since we feel no pressure, we are unaware about the air's weight. The weight of Earth's atmosphere pressing on each unit of surface constitutes atmospheric pressure, which is 14.7 psi or 1101.3 Pascal or 0.1013 megapascal at sea level. Now this pressure is called 1 atmosphere. In other commonly used units, 1 atmosphere is equal to 29.92 inches of mercury, 760 mm of mercury or 760 torr, and 1.013 bar or that is equal to 0.1 megapascal. Now since atmospheric pressure results from the weight of the overlying air, it is less at higher altitudes. Now atmospheric pressure also varies from time to time at a single location due to the movement of weather patterns. While these changes in barometric pressure, they are usually less than 1/2 inch of mercury. Now they need to be taken into account when the precise measurements are needed. Now let us talk about the gauge and absolute pressure. Now the gauge pressure, atmospheric pressure serves as a reference level for other type of pressure measurements, and one of these is the gauge pressure. Now there are two main ways of expressing the pressure. One is the gauge pressure and second one is the absolute pressure. For example, PSIA, that is the pounds per square inch absolute or bar absolute. Similarly, the PSIG, that is the pounds per square inch gauge, that is BARG or bar gauge. Now absolute pressure is usually equal to the gauge pressure plus atmospheric pressure. Now this pressure can be expressed with respect to either of these two reference points, a perfect vacuum or atmospheric pressure. Now when a pressure is referenced to that of a perfect vacuum zero pressure, it is called the absolute pressure. Now when a pressure is in reference with to the atmospheric pressure, then atmospheric pressure is termed as a zero pressure and it is called the gauge pressure. It is the pressure we normally read on a gauge. Now the relation between the absolute and a gauge pressure is illustrated in this particular figure. Now here you see that this is the absolute zero, that is 0 psi or 0 bar atmosphere. Now here this is the vacuum and it is 14.7 psi or 1.01 bar absolute. So this is the gauge pressure and absolute pressure. Now the pressure measured by the most common type of pressure measuring instrument is a gauge pressure, since this instrument indicates the pressure relatively to the atmospheric pressure. So, this sometimes referred as the atmospheric one. A tire gauge, for instance, measures the pressure in a tire over and above the local atmospheric pressure. Now, let us talk about the vacuum. And all of you, they are practically know that this was a previously used the electrical bulb. Now, vacuum is any pressure lower than ambient atmospheric pressure. The greatest vacuum possible, that is called the perfect vacuum, is zero absolute pressure or 0 psi or minus 14.7 psig or 0 bar atmosphere or minus 1.01 bar on gauge. Now, there are various utilities they are attributed to the vacuum. One is the electrical bulb. Previously, it has been used in a mass scale. Then all of us are aware about the vacuum cleaner, then a vacuum thermos, and above all in the space utilities. So, a vacuum is usually divided into 4 different levels. One is the rough vacuum. It represents the pressure between 1 millibar to 1000 millibar. Now, flow in this range is viscous as represented by most common fluids. Mechanical vacuum pumps are used for low vacuum and represents the large majority of pumps in industrial practice. Next is the medium vacuum. This represents the pressures between 10 to the power minus 3 to 1 millibar. Now, this is a transition range between the viscous and a molecular flow. Most pumps serving this range are also mechanical. Then the high vacuum. Now, this represents the pressures between 10 to the power minus 7 to 10 to the power minus 3 millibar. Now, flow in this particular region is molecular or Newtonian with a very little interaction between individual molecules. A number of specialized industrial applications such as ion implantation in the semiconductor industry fall in this particular range. Non-mechanical ejector or cryogenic pump, which are not discussed in this particular aspect, they are usually used. Very high vacuum. Now, this represents absolute pressures below 10 to the power minus 7 millibar. Now, this is primarily for laboratory applications and space simulations. Now, keeping in mind that a perfect vacuum, that is a space with no molecule or atom, is purely theoretical condition. Only in interstellar space, in this condition is approached at all closely, or even there is a few atom per cubic meter will be found. In practice, all vacuums are partial. Now, here you see that we have represented different type of application with a different type of pressure range. Like here you see that we are talking about the rough vacuum. We have the liquid jet pump, rotary plunger pump, piston pump, scroll pump, screw pump, then rotary vane pump, etc. Then the medium vacuum, 10 to the power minus 3 to 1 millibar, some sort of you can say the rotary plunger, etc., and the vapor jet pump, they are most common. Then the high vacuum, that is 10 to the power minus 7 to 10 to the power minus 3 millibar. Then the diffusion ejector pump, diffusion pump, and turbomechanical or turbomolecular pump or ion sputter pump and cryo pumps. So, all these are attributed in this particular approach. Now, PVT relations. Now, if we recall the thermodynamic behavior, then we cannot overlook the importance of pressure volume temperature relationship. These are the mathematical correlations and that develops between that only 3 measurable quantities, that is pressure, volume and temperature. Now, these are the very useful information pertaining to the prediction of gaseous behavior. Now, when we talk about the gaseous behavior, we cannot overlook the importance of ideal gas, and you see that this ideal gas equation or ideal gas behavior or ideal gas law, this is attributed to 2 laws. One is the Boyle's law and second one is the Charles law. So, the Boyle's law, this particular law describes the compression. It states that at a fixed temperature, the volume of a given quantity of gas varies inversely with the pressure exerted on it. Now, to state this particular aspect, there is a mathematical correlation that is called the P1 V1 is equal to P2 V2. Now, here this 1 represents the initial and 2 represents the final stages respectively. In other words, if we say that if the pressure on a gas is doubled, then the volume will be reduced by 1/2. The product of two quantities remain constant. Now, this is a very useful information, but again it overlooks all kind of irreversibilities associated with this particular gaseous law, like molecular interaction, and it says that the volume of the molecules they are very small. Now, similarly, if a gas is compressed to half of its previous volume, the pressure whatever it exerts will be doubled. Now, here you see this is the representation of the Boyle's law. Now, if you keep on increasing the pressure, then subsequently the pressure volume will go down. So, all these, the pressure and volume, both are inversely proportional. Now, in real gas, the real gas obeys the Boyle's law at a very low pressure or sufficiently low pressure, although the product PV generally decreases slightly at a higher pressures. Now, where the gas begins to depart from ideal behavior. Now, designers they use the Boyle's law calculation in a variety of situations when selecting an air compressor for calculating the consumption of compressed air in reciprocating air cylinders and for determining the length of time required for storing gas. So, Boyle's law, however, may not always be practical because of the temperature changes when you apply the pressure or the volumetric approach, then definitely the pressure changes will take place. Now, temperature increases with the compression, and then Charles' law applies. So, because this is again some sort of irreversibility, and that is why to incorporate the temperature effect, the Charles' law is used to predict the behavior among the pressure, volume and temperature. So, let us talk about the Charles' law. Now, the Charles' law, this law states that at constant pressure, the volume of a gas varies directly with its absolute temperature. The absolute temperature is the temperature measured with the Kelvin scale. The Kelvin scale must be used because 0 on the Kelvin scale corresponds to the complete stoppage of molecular motion. Now, measurements show that at a constant pressure, the thermal expansion of real gas at sufficiently low pressure and high temperature conforms closely to Charles' law. Now, mathematically it can be represented as V over T is equal to constant. Now, as with Boyle's law, the K is constant only for a given sample. If the gas changes, so the it changes the value at constant level. Now, here you see that if we change the volume, then the temperature profile adopts this particular behavior. Now, another law which is very important, that is called the Gay-Lussac law. Now, when the temperature of a sample of a gas in a rigid container is increased, the pressure of the gas increases as well. The increase in the kinetic energy results in the molecules of a gas striking to the wall of the container with more force, resulting in a greater pressure. So, French chemist Joseph Gay-Lussac in 1778 to 1850, he discovered the relationship between the pressure of a gas and its absolute temperature. Now, this law, the Gay-Lussac law, states that the pressure of a given mass of a gas varies directly with the absolute temperature of the gas when the volume is kept constant. Now, the Gay-Lussac law is very similar to the Charles' law, with the only difference being the type of container. Whereas a container in the Charles' law experiment is flexible, it is rigid in the Gay-Lussac experiment. The mathematical expression for Gay-Lussac law are likewise similar to those what we have studied in the Charles' law, that is P over T is equal to constant. So, P1 over T1 is equal to P2 over T2. So, we discussed Boyle's law, Charles' law and the Gay-Lussac law. Then there is a need to develop a combined law for the prediction of pressure, volume, temperature, behavior of any gas. Now, at this point, if you see that we have examined the relationship among the two of the variables, pressure, volume and temperature, while a third variable is held constant. However, sometimes the situation do arise where all three variables change. Now, the combined gas law expresses the relationship between the pressure, volume and absolute temperature of a fixed amount of gas. So, when we talk about the combined gas law problem, only the amount of gas is held constant, and this is your combined gas law, that is P1 V1 over T1 is equal to P2 V2 over T2. Now, let us talk about the Avogadros law. It is again very important law when predicting the behavior aspect of the gas. Now, we have learned about the Avogadros hypothesis, that is equal volume of any gas at the same temperature and the pressure contains the same number of molecules. Now, it follows that the volume of a gas is directly proportional to the number of moles of gas present in that particular sample. So, Avogadros law states that the volume of a gas is directly proportional to the number of moles of gas when the temperature and the pressure are held constant. So, the mathematical expression of Avogadros law is V over N is equal to constant, or V1 over N1 is equal to V2 over N2. Now, where N is the number of moles of a gas and K is as usual our constant. Avogadros law is in evidence whenever you blow up a balloon, the volume of the balloon increases as you add number of moles gas to the balloon by blowing it up. Now, let us talk about the ideal gas law, and all of us are aware that this is the benchmark for predicting the real behavior of the gaseous system, maybe a single gas or maybe a mixture of the gases, and it is very important because it provides the reference information for predicting the other thing, and by this way you can analyze or you can anticipate the behavior in a rough sketch. So, the ideal gas law, the combined gas law, shows that the pressure of a gas is inversely proportional to the volume and directly proportional to the temperature. Avogadros law shows that the volume or pressure is directly proportional to the number of moles of gas. Now, putting these laws together, this particular equation is developed, that is PV over NT is equal to constant, and that is R. That is universal gas constant, or sometimes it is referred as ideal gas constant, and the mathematical representation is PV is equal to nRT. Now, let us talk about the evaluating the ideal gas constant. The volume of 1 mole of any gas at STP is measured as 22.414 liter. Now, we can substitute 101.325 kilopascal for pressure and 22.414 liter for volume and 273.15 Kelvin for temperature into the ideal gas equation to solve R, and then R is equal to PV over NT, and let us take that we have 1 mole of gas. This is the pressure and this is the volume and this is the number of moles, and 273.15 Kelvin is the temperature. It comes out to be 8.314 kilopascal liter per mole Kelvin, or in other word, if we intend to write in SI system of unit, it comes out to be 8.314 joule per mole Kelvin in SI units, or 0.08206 liter atom per mole Kelvin, or 62.36 liter mmHg over mole Kelvin. Now, this ideal gas law shows that there are 3 ways to increase the gas pressure within a vessel or container or system. Number 1 is that put more gas in the container, for example, pumping air into the car tire. As you pump more air molecules into the fixed volume, the greater the pressure these molecules exert on the sides of the tire. So, these are the sides, and the pressure may be exerted on the higher side if you pump more and more air inside the tire. Now, second is the raise the temperature inside the container. For example, a pressure cooker. Now, as more heat is imparted into the cooker, the liquid boils and generates more vapor. The vapor gets hotter and exerts a greater pressure on the sides of the cooker, and sometimes the pressure increases due to a phase change, usually from liquid to vapor boiling, such as in this particular case. Now, third is that reduce the volume of the container. For example, a bicycle pump or piston pump. Now, packing a fixed amount of a gas into a smaller container increases the number of collision of the gas molecule and the pressure they exert on the side of the bicycle pump. This increases. So, this is again a very important aspect. In the same way, there are three ways to decrease the gas pressure and even create a vacuum within the vessel or system. One is the reduce the gas quantity, second is reduce the temperature, and third one is increase the volume. Now, let us talk about the Pascal's law. Now, this law states that the pressure on a confined fluid is transmitted in all directions. For an enclosed vessel, the gas pressure inside the vessel is constant everywhere, provided there are no isolated pockets or blockage within the vessel. When gas is under pressure, it exerts a given force against each unit of exposed area. For example, gas at pressure of say 10 psi pushes with a force of 10 pound against each square inch of surface exposed to the gas. Now, if a pressure is small, does it mean that the force exerted by it is also small? Answer is no. It all depends on the area of contact. A small pressure at larger area, if released suddenly, it can pose high force, that is impact to the body, which could be catastrophic, even life threatening. Now, let us talk about the pressure force relationship. Now, consider two circular body, let us say the body 1 and a body 2. They are having a diameter of say 3 feet and 10 feet respectively. If we apply a pressure of 30 psig on body 1, which is having the diameter of 3 feet, while only 5 psig is applied to the body 2. So, as we know that the force is a measure of pressure or pull, which can be determined by multiplying the pressure with effective area of surface where the pressure is applied. So, the area for body 1 will be pi d square by 4, and that is 3.14 into 3 into 12 inch over 4, and that comes out to be 1017.36 square inch. And if we talk about for body 2, which is having the diameter is of 10, so pi d square by 4, it is equal to 3.14 into 10 into 12 inch over 4, and that comes out to be 11,304 square inch. So, the force on a body 1 will be 30 psig into 1017.36, and that comes out to be 30,520 pounds, whereas if we talk about the force on body 2, that will be 5 psig into 11,304, and that comes out to be 56,520 pounds. Now, it is clear from this particular example that the amount of the pressure does not define the net force, and that is going to be applied. Now, let us solve one numerical problem. Now, here a balloon is designed to be inflated to a maximum volume of say 2 liter. Now, if this balloon is packed with 1.5 liter of helium at sea level, and the sea level, the atmospheric pressure is termed as 101.3 kilopascal, and upsurges to an altitude where, at which the boiling temperature of water is only 85 degrees Celsius. Will the balloon burst? Now, consider, you may take the assumption that the temperature inside the balloon do not change. Now, as this particular question is hinting about the change in the temperature, so let us first visualize the process. So, we know that the boiling point of water at sea level is 100 degrees Celsius. So if we talk about the boiling point of water decreases linearly with the rise in altitude, therefore using the cross multiplication method we can calculate the pressure at 85 degree Celsius, which is given in that particular question. So 101.3 kilopascal, say 100 degree Celsius. Now it is say, let us say that x kilopascal 85 degrees Celsius. So this x is equal to 101.3 into 85 by 100, and that comes out to be 86.105 kilopascal. Now, as we know that the pressure level at the point of consideration, so we need to know about the final volume of the balloon at that particular pressure. Now, as balloon is a closed system, and there is no change in the mass of helium, So also the temperature inside the balloon is also not changing. So let us take the help of this particular formula. P1 V1 is equal to P2 V2. So V2 is equal to P1 V1 upon P2, and that is 101.3 into 1.5 upon 86.105, and that comes out to be 1.76 liters. Now this is less than 2 liters. So obviously the balloon will not burst. That is the answer. Now again, if we take the additional aspect that at what height the balloon will burst, that means we have to take the similar data which we indicated in that in the previous problem. So here we can apply directly the Boyle's law to obtain the pressure where the final volume will become 2 liters. So in that case, P1 V1 is equal to P2 V2. Here the P2 is equal to P1 V1 upon V1, and that is 101.3 into 1.5 by 2, and that is 75.975 kilopascal. And then we can seek the help of this particular plot to describe that when this particular balloon will burst. So if we match this 75.975 to this particular plot, and that comes out to be 2600 meters. So that is this is the point, that 75.98 kilopascal, and then if we match, then it comes out to be around 26 meter. So in this particular lecture we discussed the different aspects of pressure and different terminology. We considered couple of example for the convenience, and if you need to help or if you wish to have further reading, you can we have enlisted 4 different references. You can have a look of all those references if you wish. Thank you very much.